about them we talked about limits at the beginning of the year. So basically what a limit is the value that f of x approaches, and I can't highlight that word enough. It's the value that f of x approaches. And remember, when I say f of x, I mean the y value, right? So it's the y value that the function approaches as x approaches c. Okay? So for example, if you've got this graph here, okay? If you've got this graph here, suppose you are this person, okay? And you're walking along along the x-axis towards this point C, all right? As you're walking along, you look at the graph. Now, is the graph of the function above you or below you? Above. It's above you. And as you're walking towards C, from the left of C, as you get closer and closer, is that function going further and further up or further and further down? No. It's going further and further down. And when you get really, really close to C, okay, what value does it look like that function is approaching? L.
Wait.
Okay?
In C.
L. Here.
So
as you are approaching this random number C, the value of the graph is going down, down, down towards this number L. Okay? Now, a friend of yours is here, okay, approaching that same y value. Where is the graph in relation to your friend? Is it above or below?
Above.
It's above. Now, as your friend is approaching C, is the y value going up or going down?
Up.
It's going up, up, up. And when he gets really, really close to C, what value does it look like the graph is approaching? L. So, from the left side, it looks like the graph is approaching L. From the right side, it looks like the graph is approaching L. Because the graph is approaching L from both sides, we say that the limit exists and the limit is L. So, to bring it to more practical terms, suppose this y value, that was like y equals 5. If you're looking at the graph from the left and it looks like it's approaching a y value of 5, and you're looking at the graph from the right, it looks like it's approaching a value of 5. If they're approaching the same value from the left and right, then you say the limit as x approaches C is 5. Okay? Now, in math, there are 3 approaches to solving any problem. All right? One is graphically. Next is numerically. And third is algebraically. So graphically, that's easy, right? You just like graph something and you just take a look. Numerically is you try to put in like different points. Okay, so like for example, what's the limit of this? You just put in, okay, like let's try it at 4.9. Let's try it at 4.999. 4.99999, 4.999, like you just put in points like this. Algebraically is when you do the whole thing using just algebra and the function and the variables and all that. So we're going to do these 2 today, okay, and then the next one in section 2, all right? So take a look at this. It says to estimate the limit as x approaches -7 of this function 4x plus 1 using a graph. Now, I'm going to graph this, but before I do, I'm going to modify the y-axis. I'm just going to go up by 3s instead of 1s. Okay? Is that okay with you guys? Now, this is just mx plus b. The y-intercept is 1. And then I go up 4 over 1. So if each of these are 3s, right? And if I'm going to go up 4 from the 1, I'm going to go up to 5 and then over 1, okay? So here, the slope is 4 over 1.
Just under 5.
Yeah. 6. Okay. Just under 6. So basically I went up 4 over 1. I start at 1 and I went up 4. That gets me to 5, right? But each marking is 3, so that's just right there. All right, so I'm gonna graph this and I'm gonna try to do it as best as I can. Okay, now at negative, no, so now we are looking for the limit as x approaches -7, which is here. Okay, that's x approaches -7. That's x equals -7. Okay, now as I approach -7 from the left side, and I've got my eye on the graph. What y value does it look like the graph is approaching? Do I have this drawn correctly? Okay, so hang on. Okay. X approaches -7. It looks like the y value is approaching what? Negative how much? -27. Okay, and as x approaches -7 from the right side, where does it look like the y value is approaching? -27. So now let's see if the numerical one will verify this, right? So let's plug in -7.01 into 4x plus 1. What would that give me? Anybody? Where are your calculators? So what would that give me? -27.04. And what if I plug in -7.001? Right? And what if I plug in -6.999? And if I plug in -6.9? -26.6. So as I approach -7 from the left side, my y values are approaching -27. As I approach -7 from the other side, my y values are approaching -27. Okay? So both methods then just gave me the same value. So I say the limit as x approaches -7 of 4x plus 1 is -27. Now, okay, so that's a limit. Here I have 3 different functions. I have f of x, g of x, and h of x. Okay? Now, let's take a look at f of x. Okay? Does the limit of f of x exist at x as x approaches c? Okay. Look, as x approaches c, does the limit of f of x exist? So if you go from the left and from the right, does it look like it's approaching the same y value? Yes, it looks like it's approaching L. Well, I don't care about the whole because I never. Okay, so the limit is defined as the value that the graph is approaching. We don't care whether it actually gets to that point. I just want to know where is it intending on going. As I approach C from the left and the right, it looks like the graph is going towards L, so the limit is equal to L. Okay, what about for g of x? As I approach C, does it look like it's going to the same point? Yes, so the limit for that one is equal to L as well. Okay, what about for here? As I approach C, does it look like the graph is going to the same point? Yes.
What is the difference between the 3 graphs? Yeah, I don't.
Okay, hang on. We haven't gotten there yet. Now, let's talk about what is the same between the 3 graphs. What is the same is all 3 of them have a limit of L. Okay? Are we okay with this?
Yeah.
All three of them have a limit of L. Now, let's talk about the actual value at C, okay? So, take a look at this.
Oh,
Okay, so take a look at this. If I have an X and Y axis here, okay, and here is X equals 2. What's F of 2?
it's not actually at that big.
What's F of 2? 3. Okay, so what about this one? What's F of 5? F of 5 is equal to 3. Okay? What about this one? Okay, what about this one? What's F of 2?
It doesn't exist.
It does not exist, it's undefined. So now,
There's still a limit.
okay, yes. Okay, so now we're going to forget about the limit. We're just going to talk about the value of F. So for the first one, how much is F of C? At F of C, I have a hole, so it's undefined. Okay? Okay, for the second one, G of C, at X equals C, there is a hole here, but above that, there is a point right there. So the value of G is equal to N. Okay?
So what if you have like 2 points in the same X, like 2 Y values? So then it doesn't come into
Then that's not a function. Okay, what is the value of the function here? It's L. Okay, so all this is telling us is this. For all three of them, the limit exists. Okay, but if you look at the actual value of F at that point, it could either be undefined, it could be some other value, or it could be the same value as the limit. Okay, why do we care? We'll care about this later when we talk about continuity. Yes. Okay, so let's do this, the same thing here. We want to do, we want to find the limit first using a graph. So let's simplify this one. We can factor the numerator. And what'll happen? It'll cancel with the denominator. So this will just be the limit as x approaches 4 of x plus 4. So my function just got reduced to x plus 4. What does that look like? What kind of a graph?
It's a straight line.
It's a linear equation. So the y-intercept is here, and then I go up 1 over 1. Now, what's this business, though, with the x minus 4 in the denominator?
X cannot equal.
X cannot equal 4. But now, is it a vertical asymptote or is it a removable discontinuity? It's a removable discontinuity at x equals 4 and y equals 8. So right here.
But how do we know? Oh,
So that's what that looks like. Okay. So now, using just the graph, what is the limit of this function as x approaches 4? What does it look like the limit is? As x approaches 4, what value is it approaching? 8. Okay, let's see if we're going to get the same value numerically. So now we're going to plug in our values, and we can plug it into the final reduced function, x plus 4. So 3.99 into here, it'll be 7.99. Here we get 7.999. Here we get 8.001, 8.01. So as I approach 4 from this side, I'm approaching a value of 8. As I approach 4 from this side, I'm approaching a value of 8 again. Okay? Right. So again, we verify numerically and graphically. Okay, now, one-sided limits. So sometimes it's more practical to describe the limit of the function from one side only. So just from the left side, just from the right side. But we need to have the right notation for it. So if you have, you know, the Cartesian coordinate plane like this, and if this is the left side and the right side, the left side is the side with the negative values, and this is the side with the positive values, right? So when you want to talk about x approaching c from the left side, that's the side of the negatives, we say limit of f of x as x approaches c minus, right? C from the negative side. You see that little minus there, the superscript? And if I want to talk about x approaching from the right side, it's the limit as x approaches c from the positive side.
So it would be like going from right to left.
Right. Yes. Okay? So approaching it from the right side is positive. Approaching it from the left side is negative. This box here just says exactly what I said, but I feel like my wording is better, so we're just going to use that one. Okay? All right. Using this definition then, okay? So what is the general limit then? If the limit from the left side, let's say the limit from the left side is 5. And let's say the limit from the right side is 5. Then what's the general limit? 5. 5. Okay? So this box at the bottom, you know, the existence of a limit at a point, blah, 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 just says that. So if the limit from the left side is equal to the limit from the right side, okay, and it equals L, then the overall limit is equal to L. Okay? All right. So let's do some piecewise functions. Okay, so piecewise functions, remember these split the graph into two left and right limits? I'm sorry, limits, left and right regions. So the boundary here is at x equals 1. Okay, this one time only, I'm going to do that dotted line that splits the two worlds, and then we're never going to do it again because we're growing up and we're elegant, sophisticated math students. Okay, so here, okay, now, to the right of this, to the left of this, I have this function, which is a cubic function, right? And a cubic function, you know, that looks like this, x cubed plus 2. That kind of looks like that, okay? That's to the left. To the right, I have 2x plus 1. What does that look like? It's a line. Okay, cool. That's one of those. They make us do that when we go to conferences. Okay, I'm serious. So look, you can let go of the NASA precision for most of this, but you have to be NASA precise on the boundaries, okay? So on the boundary of x equals 1, how much is the value of that cubic function at x equals 1? It's 3. 1, 2, 3. Now, is it an open or a closed circle there? Open. Oh, it's open because if x is less than 1, not less than or equal to 1, okay? Now, what about the blue? So, like the continuation of that, you know, that's just going to look like this, okay? What about the blue? At x equals 1, what's the y value? 3. Is it open or closed there? It's closed. So when they overlap, you just go and close it in. That's it. Okay? And now that is a linear graph, yes? Yep. And what's the slope of that linear graph? 2. So from any point, I just go up 2 over 1 and I have a line, yes?
Well, pretty much.
So draw that line.
At 1, right?
No, not really. You just start, okay, so.
Well, ideally, right? You have to start out. You have to start at here and then go up 2 over 1.
At x equals 1?
It can't be less than. Yeah.
So.
Well, not that you start there, but that's how you.
Okay, so when you have a line, The slope there is the same as the slope there is the same as the slope there. So you can start anywhere. I'm going to start at that closed circle and just go up 2 over 1 and there. Remember, this blue cannot exist to the left of the dashed line. Okay? So I don't go there. This is what I do. And now, we're going to wave goodbye to this little thing. We're waving goodbye. It will never come back. Okay? Never come back. Okay, so now, what is the limit? What is the limit as x approaches 1 from the left? It's 3. What is the limit as x approaches 1 from the right?
3.
So what is the overall limit?
3. That was so easy.
I know.
Tell me they don't get harder.
They don't. They actually don't.
Really? Wait, that's awesome.
Okay, so -2 is here. That's -2, yes? This is -2. So the limit as x approaches -2 from the left side, the limit as x approaches -2 from the left side is 3. The limit as x approaches 2 from the right side is -4. Because the left and the
-2, yes. Oh, -2.
because the left and the right limits are not the same,
Undefined.
it's not undefined.
Does not
exist. We do not say undefined. We say does not exist.
We do D and E.
It is DNA.
Oh.
It's a thing. DNA is a thing. Okay, here we go. The limit as x approaches 3 from the left side, as x approaches 3 from, okay, so you're this,
Positive infinity.
okay, from the left side, you're this guy walking to 3, all of a sudden you see the graph drop into an abyss to negative, to negative infinity.
I didn't want to put out like that.
As you go, this is rational town now, rational equation town. As you approach, from the right-hand side, it goes to positive infinity. Now, this is important, so listen. Left and right limits are not the same. So it's DNA. Okay?
I'm starting to think that question at the end of Mean Girls wasn't really that hard.
Yeah. So she's.
So watch. Okay, so as you approach 0 for this one from the left, you go down to negative infinity. From the right, you go down to negative infinity. Now, okay, so listen. The limit as x approaches 0 is negative infinity. However, there is a situation here. So the limit is negative infinity. Can we ever get into a spaceship, go to a location and say, okay, look, I've just gone to negative infinity? That's not possible because negative infinity is not a tangible, it's not a place that you could define. Okay, so look. It's not something you can define, so this is DNA. However, no, listen. There is a huge difference between the DNA for part D and the DNA for part C. So look at how we got DNA for part B and C. It was because the left and right limits were not the same, so it was just DNA. This one, the limit from the left and right are the same. They're both negative infinity. So for ones like this, where the limit is infinity, but you choose to say DNA, if you just write DNA without the negative infinity part, you cannot get full credit.
And if you just write negative infinity, you'll get.
If you just write negative infinity, that's fine.
Oh.
Okay? So negative infinity is okay, but DNA without the negative infinity, that's not okay. Okay. So let's take a look at this one. This is the limit as x approaches 0. Okay, so look. As x approaches 0 from the negative side, okay? What value is the y approaching? So what is it doing in this region? What is it doing? It's oscillating very, very rapidly. I have no clue as x approaches 0 what point of that range it is, right? So it's just DNE.
So, my whole test is what I'm gonna write all the answers.
I know, this is it's a common
I'll
thing.
probably get like at least half of it.
Okay, so there are several, let's just summarize the several ways where you could get, where the limit does not exist. So one is if f of x approaches different values from the left and right. Which of these examples were?
1 and 2.
So example B and C. Another one is f of x. Oh, so hang on. Sorry. This one. Look. The first one, it says it approaches different values. So that's just example B. Okay? Because C doesn't approach a value, it's infinity. So that was just B. The second one is C and D. And this one is just E. Okay, now, in all of the examples that we did, we were looking for a limit as x approached a certain value, okay? Like a finite value, x approaches 0, 3, -7, and so on. Now, we're going to talk about what happens when as x approaches infinity or negative infinity. Before, we used to call this end behavior, remember? And we used to say the limit as f of x approaches the limit of f of x as x approaches infinity and negative infinity. What it's really called is the limit at infinity. So, the way we do it is, we look at the function, and we look at the limit as x approaches infinity, and it's some value. And then, as a separate entity from that, we look at the limit as x approaches negative infinity. So now, when we're looking at the function as x approaches infinity, that's at the far end of the positive. And then at negative infinity, it's at the far end of the negative. So the two have nothing to do with each other. They're at like total opposite ends of the universe, right? So they're different entities. We don't try to compare them. We don't try to see what happens if the limit from, this and this are the same. There is no such thing. They're just two different things. Okay, so let's take a look at this one. The limit as x approaches infinity, okay? So if I'm here and I'm walking towards infinity, positive infinity, what y value is the graph going to take on? Just -3. And as I approach negative infinity, -3. Okay, so that's what I'm saying. There is no such thing as the overall limit because these are like at different ends of the universe. They're different entities. Okay, here we're looking at x equals positive infinity. Okay, so as x approaches positive infinity, right? So what's happening here? It's gonna be somewhere between positive and -1. Do I know where exactly? No, so it's DNE. Okay.
Oh, whoa, I like that one.
Okay. Okay, so now, hang on. So here, this one, do you see how the function looks very different from the left and from the right? So we're looking at what happens as x approaches infinity here. It's oscillating very, very rapidly. We don't know where it's going to end up. So it's DNE. But as I approach here, the limit is 0. Okay? So I just wanna say something else here. Just a little bit of, just a little bit else here. So look at this function. It's e to the x sine 3 pi x and so on and so forth. So look, if I do like the envelope of this here, that's e to the x, okay? And if I do the envelope here, that's negative e to the x, okay? So what this used to be is this used to be a sine function, but now the e to the x takes over, and what it does is it reduces the curves